Okay, number 11 on the McGehee problem set. We got a 4-kilogram sack of mail sliding down a 6-meter long mail chute, which has a vertical drop of 2.5 meters. So I got a little diagram here, and we're told a constant friction force of 10 newtons acts on the sack as it slides down the chute. Now, as a reminder, one thing we know about friction is it's always opposite motion and parallel to the surface. So as the box slides down the incline, the frictional force, the frictional force is going to be back like this. And it's a constant frictional force of 10 newtons. Now, first question, what is the work done on the sack by friction? Well, what's the basic equation for work? Work is force times displacement. And what has to be true when you're using the work equation? The force and the displacement must be parallel. Now, so if we're looking for the work of friction, we're just going to take the force of friction times the displacement. And we have both. So this is pretty easy. So the frictional force is 10 newtons, and then the displacement is 6 meters. So this gives us 60 newton times meter. Now what's a newton? What's a newton times a meter? A joule. So the work done by friction is, now we got to make it negative, because look, what's the sign convention for work? Work done in the direction of motion is positive. Work done against the motion is negative, and friction is always against motion, so we're going to make it negative, Or you could just look at it like this. We're saying down the hill is plus and up the hill is minus. Friction is negative, so we can just plug it in right here. Negative 10 newtons, okay? Now, part B, how much does the mechanical energy of the sack change as it slides from the top to the bottom of the chute? From the top to the bottom, how much does mechanical energy change? Well, look. What is mechanical energy? When we say mechanical energy, what do we mean? We mean the sum of three things. Mechanical energy is kinetic, it is potential of gravity, and it's potential of spring. So look, in this big master equation that I have here, this circle would represent mechanical energy initial. This circle would represent mechanical energy final. Mechanical energy initial and mechanical energy final will be the same unless what? Unless there's a force other than gravity or spring doing work. Do we have a force other than gravity or spring doing work? Yeah. We have a force other than gravity or spring, and what is that force? Friction. So guess what? What's going to be the difference between mechanical energy initial and mechanical energy final? The difference between those is going to be this right here, which happens to be what? What is the non-conservative force here? Friction. The work of friction, and this is going to be, are we going to make this plus or minus for this problem? Is it plus or minus? Minus. So what's the difference between the starting mechanical and the ending mechanical? It's the work of friction, which was negative 60, right? Basically, guys, friction stole 60 joules of mechanical energy. Is friction ever going to give you more mechanical energy? No. Never, ever, ever. All right, last question. If the sack is given a speed of 9 meters per second, so now we start with V initial, 9 meters per second. What will be the velocity of the sack when it reaches the bottom of the hill? So here's how we do it. We're going to use the big master equation. Do we start with kinetic initial at the top? Yeah, it's moving. Do we start with potential of gravity? Yeah, because I have the 0 point down here. Put the 0 point at the lowest point in the problem. This is the 0 point down here. So we have potential of gravity. Any spring energy? No, there's no spring up here. Do we have work non-conservative? Yeah, in fact, we know what that is. It's negative 60. That's the work done by friction. Okay, down here. Do we end with kinetic? Yes. Potential of gravity? No, because it's on the 0 point. Potential of spring? No. So here's what we got. We got kinetic initial plus potential of gravity initial minus the 60 joules that friction took away equals the kinetic final. Okay, so you plug in the equations. You go 1/2 mv initial squared plus mgh minus the 60 equals 1/2 mv final squared. So this right here, the 1/2 mv squared is 162. The mgh is 100. And then we got 60. So the only thing missing here is v final. So you solve for v final and you get 10.